Hello students, this video is to help you out with lesson 6 from unit 12, the unit on sequences. I'm going to go over some of the problems from the problem set, and I'm going to try to answer some questions that were emailed to me. Taking a look at the first problem, it says the culture of bacteria doubles every 2 hours, and we know that doubles indicates to us that it's multiplying by 2. If there are 500 bacteria at the beginning, and we know that 500 bacteria is the starting value, how many bacteria will be there after 24 hours? The first thing we're going to do is create a table that models the scenario. Pause the video, try to make that table, and come back. Hopefully you filled out the table correctly. It should have been 0, 2, 4, 6, 8, keeping in mind that it's doubling every 2 hours, so these hours should go up in increments of 2. The sequence is geometric, and we know that because the sequence features multiplication. If we were to write a recursive formula to model the situation, we'd need to know a little bit more information. Right now we have the number of hours at 0, the number of hours 2, the number of hours 4, but we don't know the amount of bacteria at 1 hour. So there's a way to figure that out. I'd like you to try to figure that out first, pause the video, and then come back and we'll talk about it. Alright, the question that I just asked was, what is the value of a sub 1? We're looking for the first term. So if you don't know a sub 1, there are a couple ways to get it. One easy way to find a sub 1 is to try to use the backwards division method. And here's what I mean. So if you start at 500, you don't know exactly how much you're multiplying by in order to get from 500, which is a0, to a1, which is the first term. And you don't know what you're multiplying by between that number and 1,000. But you do know you're multiplying by the same number. We call that number r the common ratio. So we'll represent that with the letter r. So here is multiplication by r, and here's multiplication by r. So in other words, we don't know exactly what the number is, but we do know that if you take 500 and you multiply it by r, and then you multiply it by r again, you'll get 1,000. Because, because we're multiplying by that common ratio twice. So in other words, we can say that 500 is equal to, 500 times r again should be equal to 1,000. The next step is to try to solve for r, get r by itself. So we know that in order to get r by itself, we need to divide both sides by 500. So we have r times r is equal to 1,000 divided by 500, which is 2. So far so good. We have r times r is equal to 2. We know that r times r, in other words, is simply r squared. So we can represent this as r squared is equal to 2. Well, in order to get the value of r, it seems to me that we should just square root both sides. So the answer for r, the value for the common ratio, is not 2, but the square root of 2. Again, the way we calculated that is knowing that we know that from 500 to 1,000, we're jumping not once but twice. And we know that 500 times r is equal to 1,000. Solving that equation gives us that common ratio. So, now that we know the common ratio, we're able to determine the first term. Take that common ratio and try to figure out what the first term is. Pause the video and come back when you're done. Alright, if you use your calculator, which I did, you get a weird crazy number like 707.106, etc. That is an irrational number. So we're not really going to use that in our equation, but we can use another value. We know that this value is equal to 500 times radical 2. Well, it seems to me that we could just use that value, and that could be our a1. So we know that our first value is simply 500 times radical 2. Whoa, that was weird. Alright, now that we have our first value, which is 500 radical 2, we can get rid of a little bit of this work. We can get rid of all of the planning that we did here, and we can try to determine what the recursive formula and the explicit formula are. We know that the first value is 500 radical 2, And we also know that the common ratio is radical 2. Try to take the next couple minutes to write a recursive formula and explicit formula and come back and check your work. All right, check your answers. We know that the recursive formula has two parts, the starting value and the pattern. And I'm telling you that the starting value is 500 radical 2, and the pattern is take the previous term, multiply by radical 2 to get the current term. We also know that the explicit formula only has one piece, but it's composed of an equals a1 times r to the n minus 1. So now we're done with the recursive and explicit formulas. Now we can answer what the question is asking. It's asking how many bacteria will there be after 24 hours. So what we have to do is use 24 as our value, as our number of hours. As soon as we're done with this method, I'm going to show you a slightly easier method, but I'd like you to try this right now. Try to answer what the question is asking by substituting 24 into the explicit formula. All right, looks a little messy, but we were able to figure it out. We took the explicit formula, we substituted in 24, and remember, you took my advice and substituted 24 and then subtracted, and then took all of this and put it into the calculator. Calculator gave us 2,048,000, so 2,048,000. So we could write that in, 2,048,000. And remember, the question was asking about bacteria. So you could say there were 2,048,000 bacteria after 24 hours. Now, I told you that I was going to show you an easier way, and it requires a little bit of, a little bit of fakery on our part. I want you to notice that this refers to the number of hours, and this refers to the number of bacteria. So the number of hours goes 0, 2, 4, 6, 8, etc. The number of bacteria goes 500, 1,000, 2,000, 4,000. So we know that the pattern for the bacteria is multiplying by 2. Wouldn't it be nice if the number of hours didn't go up by 2s, just went up by 1s? Then we wouldn't have to deal with this radical 2 nonsense. Then we'd be able to figure it out a little bit more easily. It turns out that we're able to change the problem to suit our needs. Instead of saying number of hours as my x value, or in this case my n value, I'm going to say that my n value is going to be the number of 2-hour periods. Let me say that one more time. I'm going to change the number of hours to the number of 2-hour periods. So here's a table that describes what I was talking about. The number of 2-hour periods starts at 0 because we're starting at 0 anyway, and the number of bacteria is 500. Then after one 2-hour period, in other words, after 2 hours, the bacteria grow to 1,000 different units. And then after the second 2-hour period, which in other words is 4 hours, we're at 2,000 bacteria. The pattern goes on like this until, well, we're trying to find 24 hours, so we would need 12 2-hour periods. Try to figure out how you would use this pattern or this scenario and an explicit formula to try to figure out how many bacteria there are after 24 hours. Pause the video now and come back to it and you'll check your work. All right, hopefully you identified the fact that this 1,000 is our first term because after one 2-hour period, we're looking at 1,000 bacteria. Hopefully you also identified that from this 2-hour period to this 2-hour period, we multiply by 2, multiply by 2, multiply by 2, etc. So that 2 is our common ratio. You can see that I went from the generic form or the explicit form to a specific case where we went past 12 2-hour periods, in other words, 24 hours. You should also see that we took the 12 minus 1 and simplified it to 11 before we put it in the calculator. And lo and behold, when we put it in the calculator, we got 2,048,000, the same as what we got from this ridiculous nonsense with the square roots. So what I wanted you to see is you could do the problem either way. You could do it using the information that they give you, or by slightly changing the problem so that it was a little bit easier to work with. But if you had decided to change the problem so it was slightly easier to work with, well, it was slightly easier to work with. Alright, looks like in this video I'll have time for one more problem. So I'll do the second problem wherein they talk about the radioactive material. Now, one thing that you might remember is half-life. Half-life is something you might have learned in earth science or maybe even living environment. The half-life means we're decreasing by 1/2 or 50%. That is an exponential decay function. So we know that the sample starts off with 500 milligrams of radioactive material, and the half-life is 1 day. So after 1 day, we only have half of the material left. Incidentally, this is not a realistic situation because most of the time half-lives are measured in hundreds and thousands of years. Find the amount of radioactive material, the sample at the beginning of the 7th day. Well, it's the beginning of the 7th day that we're looking for, so try to make a table, try to make an equation, and pause the video, and then come back and check your correct answer. Alright, the theme of this lesson was using equations or functions and using formulas for sequences should give you the same answer, and I wanted to show you that this is yet another example. If you decided to go the function route, you would have seen that 500 milligrams was the y-intercept. It's the starting value. It's what happens at the beginning. You know that 1/2 is the base or pattern because half-life means you're decreasing by 1/2 or taking away half of the substance. So we're able to write our exponential function as 500, the y-intercept, 0.5, which is the same as 1/2, the base, to the x power. If you had decided to go the sequence route, you would have known that 500 milligrams is this mythical A0 that we don't really use in sequences, but it helps us find the first term, the first value. 1/2 is the common ratio, and remember that the base or pattern and the common ratio are essentially the same exact thing. This calculation, the only reason I had to do this was to find the first term, A sub 1. I couldn't use 500 milligrams in my sequence formula because A sub 0 doesn't make sense in terms of a sequence, but A sub 1 does. A sub 1 is the thing that we use to build the whole sequence. So we take 500 times 1/2, we get 250. And then 0.5 is that common ratio, and n minus 1 is the exponent. I want you to see that what I did from here, the exponential function, to here, the geometric sequence, is I basically just multiplied this this starting value, that A0, by 1/2. In other words, the 1/2 that I didn't multiply here, I did multiply here. If you can see that, great. If not, that's okay. You can still use either one of these tools in order to get the correct answer. Pause the video right now and do the calculations and see if your answer is correct. Alright, it's a happy day in Mathville because what we just found was that 3.90625 is the correct answer for both of the evaluated equations. Both the function, the exponential function, and the geometric sequence formula gave us the same answer, which is good because it's doing the same thing. We're multiplying by 1/2 every time. The only difference is where we're starting from, whether we're starting from the y-intercept, where x is equal to 0, or from the first term, where x, or n, or the input, is equal to 1. Alright, that's about all the time I have for this evening. Good luck studying.